The next problem involves small signal modeling. This is the topic of reading assignment 2, number 3 in exercises. And the problem gives you a series RLC circuit like this. It doesn't tell you what the state variables are, but it tells you what the input and output are. The input is this voltage source right here, V. You're also given its operating point. It's equal to VDC. You are also told that the output is the power delivered by the source to the circuit. And you're asked to find the state space equations for this circuit and the output equation, and you're asked to solve for operating points for the inductor current, which is also the current through everything, for the voltage across the capacitor, this one, and for the output, which is Pin. Turns out I1 and Vc are the state variables, so essentially you're told find operating points for the state variables and output when you're given the operating point for the input. And those would be called capital I1, Vc, and Pin. So just a reminder, the operating points for everything in this problem will be just capitals, except for this V, which would be called VDC. Okay, so let's do part A. We know that, let's start by state space equations. We know that state space equations come from differential equations, and the reason we'll have differential equations involved is because of the inductor and the capacitor. The relation for the inductor is L di dt equal to VL, where VL is this voltage across the inductor. And the relation for the capacitor is C dVc over dt equal to the current flowing into the capacitor, which is the same one as the current into the inductor. So it's also I1. Now, by figuring out what this VL and I1 are in terms of state variables, you're going to get the state space equations. Now, you see that the state space equations should be in a form like this, where you'll have the derivatives on the left-hand side, and then everything else on the right-hand side should be in terms of this guy and this guy, and also in terms of the input. So this guy is the input. And those are state variables, I1 and Vc. So what do we have here? Here we already have I1, well, over C on the right-hand side. So this guy is one step away from being what we want. With this guy, we need some work because we have this VL, which is not a state variable. But we can use Kirchhoff voltage law to figure out VL in terms of everything else. So you see here that let's make a loop like this one. So we'll have plus V minus voltage drop over the resistor, which is going to be equal to R times this current. So V minus RI1 minus VL minus Vc. So I'm going to write it here. It is V minus RI1 minus VL minus Vc equals 0. So then from here we can solve for VL. It's going to be equal to V. So I'm shifting this to the right hand side and then swapping the two sides. We'll get V minus RI1 minus Vc, and that's it. So then the next step is to take this and plug that back into here. And then you see V is the input, I1 is the state variable, and VC is the state variable. So this, the next step would be to take this guy and this guy divided by L and C. What we'll get is this. So on the left-hand side, we'll have di1 over dt equals to, then you see this L ends up being in the denominator of everything. And then here we have, let me use a highlighter. Here we'll have negative Ri1 minus this one, which is from here, plus V over L. Then this one is just the same thing as the state equation, except we need to divide by C. So that's what we got here. Now, for the output equation, it's a bit more simple because the power in, we just know it's in terms of V, which is the input, times the current going into the circuit. So this I1 times V is the power flowing into the circuit. That's what we have here, and then I just copied here. I swapped I1 and V because I'm a bit more used to having inputs the closest to the right as possible, just easier for me to read. Okay, part B asked you for the operating point. Operating point means that we are setting all the time derivatives to 0. Actually, well, this maybe let's work on this one. So all of these time derivatives would be set to 0. And also, yes, so that would allow solving for state variables operating points. So I set the left-hand side to 0 here and here. And then I got this equation. You see how all the smaller case quantities turned into their corresponding DC operating points. And then we have this guy is given. And then we have unknown here. This guy and this guy is the same, so we have two equations, two unknowns. Let's solve it. From here, we just have I1 equals 0. And from here, we have this guy now is 0. So we have negative 1 over L VC plus VDC over L equals 0. We can remove the L, so multiply both sides by L, shift VC on the right-hand side, or all the way around, and then we'll get VC equals to VDC. This is operating point for VC. This is operating point for I1. And then, I don't know what that is. Sorry. I'll actually, okay. I think I just typed up what I just wrote. Let me just get rid of it. Sorry. Okay. So now for the output, the DC operating point is just, you just get it by plugging in DC values for this guy. So it's going to be this VDC times I1. Now it's these values, this is how you find operating points in general. If you have sort of arbitrary differential equations like this, state space equations and output equations, and I just tell you, I just give you a DC operating point for one of the variables, very often the input would be the one that's given. And then I ask you to solve for everything else. This is the standard procedure to do that. Now, since this is a circuit, another way to get these values would be like this. Just short out the inductor, open up the capacitor, because that's exactly what happens at DC. So then what you get is a circuit like this. So you have, well, let me make it a DC source, VDC, then you have your resistor, then you have the inductor that's shorted out, and you have the capacitor that's opened up, ground, ground. So here's what's happening. The voltage across the capacitor is going to be the same as this voltage because, actually, let me call it capital VC equals VDC because there is no current flowing here. So voltage drop across the resistor is 0. And the current is 0. We know there can't be any current flowing through this circuit. So again, I1 would be 0 and VC would be equal to the input. And that's exactly what we got. I1 is 0, VC is this. Okay, in the next part, you're asked to find a small signal model at the operating point that we just found. Here, I've copied what I got on the previous page, the original equations without any small signal approximations. And then the small signal model, as you learned from class, oh, why is it so? Okay, yes, sorry. The small signal model, which you learned from class, is given by this and this. Let me explain what each of these mean. So the hatted quantities mean perturbations with respect to the operating point. So you have some DC current, and this is, you know, plus minus 0.1 milliamps or something like this, and your actual DC value would be some other value. And this also perturbation with respect to the DC operating point. And you see how this is a matrix equation. We have this one input variable here, and there is two equations here. So this matrix, for example, would be 2 by 1. This matrix would be 2 by 2 because there is 2 rows corresponding to these guys and 2 columns corresponding to these guys. The output equation would be, oh, sorry, this should be hat. 1 second. So the output equation would be like this. This is the perturbation of the power, output power, sorry, input power actually, but it's like output equation. Because of the perturbation of these other variables, and you'll have, again, these matrices. Because there's 2 state variables, you'll have 2 columns, but there would be only 1 row because this is only one output variable involved. And this guy would be 1 by 1. Now, here's how to find these matrices. What you need to do is you need to find derivatives of these functions. Remember, this is f1. This is f2. And this is g. And what we need to get is partial derivatives of each of these guys with respect to state variables and with respect to the input variable. And they should sort of correspond here. Let me show you. So f1 would be in the first row because this is the one that's involved in this equation. So we have f1 here, f1 here. And f2 would be, let me just use the same highlighter. F2 would be in the second row. This one and this one. Now, derivative with respect to I1 would be in the first column, and derivative with respect to VC would be in the second column. Now, all of these derivatives would need to be evaluated at the operating point. So that's why I have this I1 equals capital I1 and these guys equal to their DC operating points. So essentially, we'll find the derivatives and plug in the DC operating point. So this was GF. Let me explain BF. It's very similar, except Now we are looking for derivative with respect to the input instead of the state variables, because here we're multiplying by v hat. So we'll have derivative with respect to v, and again, first row is f1, second row is f2. For the output equations, similar idea. We have jg, sorry, should be g, equal to, here we have g involved, where g is this guy. And again, first row is going to correspond to I1, second row to VC. Again, everything evaluated at the DC operating point. For B, everything is the same as this guy, except with respect to V hat. So we have this here, and then again, this is G. Now let's find these matrices. We need all the partial derivatives. So for GF, we need derivatives of F1 and F2. This one, let me actually copy it. So it's negative R over L I1. No, let me just differentiate it. Sorry. Okay, so we need derivative of this with respect to I1. This would be negative R over L, right? Because everything else, this variable and this variable wouldn't matter for this derivative. They're just constants. So this first derivative is negative R over L. Derivative with respect to VC is going to be negative 1 over L. Derivative with respect to this V is 1 over L, because everything else is a constant. For F2, we have derivative with respect to I1 is 1 over C. And then all the other derivatives are equal to 0. So let me fill in this matrix and this matrix. So this would be, in the first row, we have derivatives of F1. So it's negative R over L and negative 1 over L. And then this guy is with respect to input, it's 1 over L. For F2, we have 1 over C, 0, and 0. It's really noisy outside my apartment, so I really hope you guys don't hear all the noise, because it's driving me crazy. If it's driving you crazy, I'm sorry. Okay, output equations. This is a 1×2 matrix. So we have derivatives of the output equation. So it's VI1 or I1V. Derivative of G with respect to I1 is given by V. Derivative with respect to VC is 0. Oops. And derivative with respect to V is I1. Now we want to plug this all back in. So this derivative is going to go here. We have V, but we need to be careful. It's not just V. We actually need to evaluate it at DC operating point, right? So instead of just V, we plug in its DC operating point. And then here we have just 0. And then here we have I1, but again, we need to evaluate it at DC operating point. So it's this one. Because it's a matrix that's a constant. So the only non-constant thing in this set of equations is the hatted quantities. These matrices need to be constant. Here, we didn't have the issue with having to plug in anything, because we already had these derivatives as constant. Here, derivatives weren't constant, so we needed to actually plug in the DC operating point. So that we can make these matrices constants. Is this on the page? Yes. Okay, next page. So, right. Okay. Sorry. So, so this actually answers all the questions. So, so in terms of problem solutions, this is it. It's done. I just want to point out one thing. It's this. So we had the original equations, this one and this one, state space and output equations, and they were, this is valid for any magnitude of these quantities, and it takes into account some DC offset and everything. So these guys are exact. Then we replaced all the variables with their perturbed quantities. So we had our I1, which was first written like this, plus I1 hat. Then we had our VC that was written as DC plus perturbation. And then we had our, what was it called? V, which is the input, written as its DC point plus perturbation. And we also had output, which was again written as the DC plus perturbation. So this is smaller case, this is capital. Now, this is not an approximation in any way, it's just replacing one variable with something that's easier to work with in some problems. And that's how we got all those equations with hats. Not here, on the other page. These equations with hats. But there is some approximations involved, and I'll tell you where. So approximations come when we are dropping when we're turning a nonlinear equation into a linear equation, essentially. Here's where it happens. And it happens actually, in this case, only for the output equation, and it doesn't happen for the state space equation. So state space equation, when we got our small signal model, we didn't actually make any approximations. It's going to be exact no matter how large the perturbation signals are. So if this guy, V hat, is very large and making these perturbations very large as well, the model is still valid. It's not the case for the output equation. Now, why do I say this? Let me explain. This happens because F1 and F2, which were involved in state space equations, are equal to their own Taylor expansion. And this is not the case for G, the one that's involved in output equation. Let me show you. Just a reminder, Taylor series expansion in this multivariable case is so this is from lecture slides. It's for lecture 8, it's equal to DC operating point. Well, the DC value of this F1, which by the way is 0, but we don't need to worry about that for this particular page, plus derivatives with respect to everything, so all the variables involved, so you see U1, U2, and then we have X1, X2, everything, all derivatives, times their corresponding perturbation. Perturbation of U1 multiplying this derivatives, perturbation of U2 multiplying that derivative, etc. And everything here is for F1, right? And then for the second equation, we'll have the same thing with F2. So let me do it for this particular case. Here, I just copied these guys from the previous page. previous page. And then I'm plugging in everything that's important. Okay, this guy is the DC value. So it's just F1 with DC values for variables plugged in. Remember, F1 is right here. When I plug in I1 capital, VC capital, and VDC capital, that's what I get here. And then I need to I need to add all those derivatives times their perturbations. So this derivative, and this derivative times I1 hat, VC hat, and V hat. Same idea here. We have the DC point, 1 over CI1. This is what I got by plugging in I1 capital, plus 1 over C I1 hat, plus 0 VC hat, plus 0 V hat. For the output equation, same idea. I'm plugging in DC value right here, and then I'm adding contribution of the perturbations. So this would be, you see this derivative, VDC, except remember, when we're finding Taylor series expansion, we need to find derivative and evaluate it at the expansion point. So this is exactly what I'm doing here. And then times corresponding perturbation I1 hat, and then plus, well, I didn't put the term corresponding to this because it's 0. And then we have I1 capital, value of the derivative, times corresponding perturbation. So it's the same thing. This Taylor expansion is the same thing as we do always when we evaluate f at x plus delta x as f at x, well, let's call it bar, x bar plus f prime at x bar times delta x. That's essentially what I'm doing. I'm taking perturbation times derivative plus DC value. Okay, so, oh, by the way, I said DC value is 0, but that's only for these guys, not for this. This is not 0. Okay, now let's compare this to the F1 and F2 values. You see this guy plus this one is the same thing as negative R over L times the entire I1, because you see perturbation plus DC value. This is this guy. Then we have minus 1 over L VC capital, and we have this one. This is exactly equal to this one. And then this part, the remaining part, is VDC plus V hat over L. Well, let me choose different highlighter. So this is the same as this. For this guy, same idea. We have 1 over C I1, and here we have 1 over C times I1 hat and I1 capital. Everything else is 0. So then for the state space equations, we can actually write exact equality. We don't need to write approximation. Now for the output equation, this was not the case, because here you see that we have this is equal to, well, I1 VDC I1 V, so we have I1 times V plus VDC I hat 1. And this is not the same thing as this guy, because this guy is equal to I1 plus I hat 1 times VDC plus V hat. If you expand this, you're going to have 4 different terms. one of which is going to be this, no, sorry. Well, one of which is going to be this one. We will have VDC times I1 hat, it's this one. I1 V hat is this one, but we're missing the fourth term, which I think would be this one. So I hat V hat. This guy is missing. So that's why this is an approximation here. Now we know that this is a small value, this guy. I hat V hat. I1 hat V hat because it's two perturbations multiplied together. But the reason why this is not an approximation and this is an approximation, why here we have approximate equality, is because here in Taylor expansion we're neglecting second order derivatives, but second order derivatives are actually zero because any of these guys differentiated with respect to anything would give you zero since it's a constant. Here, however, if you differentiate this guy, for example, with respect to v, so you'll have dg, this derivative is equal to 1. It's not equal to 0. So then, because of this, Taylor expansion is actually an approximation. Also, another way to explain why this is happening is because here the original equations are not involving any products between state variables or any terms with squares, but then here we have state variable multiplied with the input. And then this can be basically traced to why this derivative is doing this. Let's do question 63 from 16.1. The question tells you that partial derivatives, second order partial derivatives of f are continuous on a region given by this, what I'm showing here. X in this region is going from 0 to a, and y is going from 0 to b. So the region is a rectangle like this. And the question asks to simplify this second order partial derivative of f with respect to x and y. So let's do this. This I'm writing the iterated integral over x and y. Y is going from 0 to b because these are the bounds on y. X is going from 0 to a, so 0 to a. This I'm writing the partial derivative. I sort of expanded it in this form to see better what's differentiated which way so that we can integrate in the next step. Next, I'm integrating with respect to x. Integral with respect to x is going to remove this derivative, and then we need to evaluate it at the endpoints, so x equals 0 and x equals a. Then next, I'm rewriting this as this function, which in itself is a derivative at x equals a and y being arbitrary, and then same thing here, but now x equals 0. Then I just broke the integral into two parts, and then I integrated. So when I integrate with respect to y, the antiderivative would just be the function f. So we need to take f at ay, at y equals 0 and y equals b. These are the endpoints. For this second integral, it's the same thing, but now x equals to 0 instead of a. And then I'm expanding this as fab minus fa0 by plugging in y equals b and y equals 0. This guy is equal to f at 0b minus f at 0, 0. So then I have minus f at 0b plus, because these negatives cancel, plus f at 0, 0. Now, the part that could have been a bit confusing is this integration, how we're treating y as a constant, and this removes this derivative, but this derivative is just a function. If it was confusing, maybe I'll do an example of a specific function so that you understand what each of those derivatives mean. Okay, so here I'm choosing function like this, exponential. The exponent is 2x plus 3y. Derivative with respect to y would make, sorry, what did I write here? This should be 3. Yes, so derivative with respect to y is going to create this 3 here, and then derivative with respect to x and y is going to be 3 times 2 times the exponent. Then I'm integrating this whole thing. First thing that happens is we integrate with respect to x, and then we get this in the integrand. What this is the partial derivative of f with respect to y. Let's check that this is the case. This is the partial derivative of f with respect to y, so everything matches up so far. Then in the next step, I'm evaluating this as usual at x equals a and x equals 0. Then in the next step, what I did is I broke the integral into 2 parts. Then I integrated with respect to y, which removes this 3. So then I get, you see this guy is f. This guy is f at ay, and this guy is f at 0y. And then what I get is, by evaluating at the endpoints, I get f at ab minus f at a0 minus f at 0b plus f at 0, 0. So everything matches up, as I said here. Well, I only checked some of the steps, but you can see I didn't mess up, hopefully. Problem 63 from 16.2. The question asks you to evaluate this integral. Now, if you try evaluating it by integrating dx, you will not be able to proceed because you cannot write antiderivative of this with respect to x in terms of elementary functions. So the only other option, at least the one I'm seeing, is to swap the order of integration. But first, we need to figure out what the region of integration is. You see the region of integration goes for y from y equals 0 to 1. So from y equals 0 to y equals 1. And from x equals y to x equals 1. So this would actually intersect right here. So again, y going from 0 to 1, and for every value of y, we go from this line, x equals y, to x equals 1. So we integrate over this region. Now what we will do is to swap the order of integration. So we would integrate like this. So we will have x going from 0 to 1, And for every value of x, we're going to go from y equals 0 to y equals x. And the integrand is the same. And now instead of dx dy, we have dy dx. Then we can integrate with respect to y. This guy is a constant as far as y is concerned. So we get e to the x squared times this distance from x to 0. Sorry, from 0 to x. So we get this. And now that has antiderivative with respect to x that we can write down. So this would be e to x squared, but not quite, because when we differentiate, we'll get 2x. So we need to divide by 2 to fix it. So this would be antiderivative. And bounds are 0 to 1, so we get e to the 1 squared, so e minus e to the 0, which is 1, divided by 2. Now, in the textbook, you're actually told to reverse the order of integration, but I think you should be able to, after enough practice, you should be able to know when it's a good idea to swap the order of integration and when you should try and evaluate directly.